non-generating function. For x, random variable, psi x of t is how we denote the MGF, non-generating function. To define the expectation of e power of t. And then we looked at how this can be of use to generate or derive different models. In particular, the mean and variance can be easily obtained from this. So sometimes this way of computing moments will be useful to us. In particular, we looked at the Bernoulli random variable. See, we looked at the MGF for certain random variables x, Bernoulli, property p, then psi x of t we derived it to be p e power of t plus 1 minus p. That again follows simply because if you put this one, x can take only two values 0 or 1. It is 1 minus p into e power of t into 0 plus p into e power of t into 1. That is what you get, p e power of t plus 1 minus p. This is for Bernoulli. For binomial of n Bernoulli tiles with the property of such being p, we can derive using that np, n choose p and so on. Or we know that it is a sum of n Bernoulli random variables. So the MGF of this binomial random variable will be the nth power of this. Because if you sum two Bernoulli random variables, if you want to find the joint density function of it, you have to do convolution. But when it comes to the MGF, it is just the product. And it holds good not only for 2, for any number n. It's an n-fold convolution will be very difficult to compute the joint density function. Whereas the corresponding MGF is very simple, just the power. For if x is Poisson parameter lambda, then the MGF is e power of lambda e power of t minus. This also I derived it in the last lecture. You have to recall. I am just recalling because we are going to use it. Now the most important thing is the normal or the Gaussian distribution. That is what we are going to do. It's MGF. So we will start with the standard normal distribution. Normal random variable. What is it? N of 0 comma mean 0 variance 1. And what is the, if x is standard normal, then what is fx of x? 1 over root of 2 pi into 1, which will not go, e power of minus x minus 0 the whole squared by 2 x squared. So this is the density function of the standard normal. So for that we have to compute the MG. By that I mean standard normal distribution. So what is it? So because we are using the general notation x for all random variables, different random variables having different distribution will have different NGA. To denote it, I am using this convenient symbol, so you know what it is. X burn, this is x burn. And that is x binomial, and so. Again, it is the SDN. I will put it as it's not any norm, standard norm. So it is expectation of e power of Tx. That is equal to expectation we have to do for normal, which means that it goes all the way from minus infinity to plus infinity. And then this is the function for which we are taking it. So it is function g of x. So it is g of x into fx of x. What is g of x? E power of t into x. Fx of x of SDN, which is 1 over root of 2 pi into e power of minus x squared by 2. So we will take out root of 2 pi here. So this is what we have left, which we have to compute it. So what we will do is we will use a trick which is called as completing the square. We will like to have a square of something in the on the x term, on the top of the x. To do that, one first step is e power of minus x squared by 2 into e power of 2tx by 2 into dx. This is the first step. Then we will club it. Yeah, this is what we get. But what I am looking for, this is an expansion of by x plus y by whole square, but one is missing. The square term is missing. Okay. What is x? T squared x squared is missing. So we will introduce that. So what we want is actually inside this one to make it as x minus t the whole square. X squared is there, minus 2tx is there. Minus what we want is plus t squared by 2. We want here. To get that one, there is a minus. So if we have minus t squared by 2, if you club it together, here you will have plus t squared. Then it will become a square. Correct? To compensate for something that we have introduced, we have to introduce. So I have not done anything extra, I am just multiplying this and this. But now we will take this one out and we will come join this together. This one we will take all the way out. Okay? Because this only an the dx is the variable. T squared can be taken into 1 over root of 2 pi. E power of minus these two things. Okay, I can write it as x minus t the whole square. Right? Into dx. By doing that, I have transformed this integration into this. I did it with a specific purpose. Why? What is that purpose? Because this is something which we will be able to easily do. How much? What will be the value of this integral? Huh? It has to be 1. Because this is a Gaussian integral. Okay? It's a Gaussian integral. of a Gaussian random variable with mean t and variance 1. Because look, root of 2 pi sigma squared becomes 1, and here also your sigma squared 1 comes, but if it were mean is t, x minus t whole squared by 2. Only difference is that they had mean 0, it had mean t. Both had sigma 1. So it's also Gaussian integral. If you do this kind of a Gaussian integral, it has to be 1. You don't need to worry about looking at everything. So this is just 1. So what we have, e power of t squared by 2. So we have got the NGF for the standard S and B. Standard normal. We have got the NGF for the standard normal. But we want it for an arbitrary Gaussian with some mean, some variance. Okay? So how do we get it? We know that if we have n mu comma sigma squared, a arbitrary Gaussian distribution with mean mu and variance sigma squared, we will call this as x. Then if you put a transformation, we can convert it into standard normal. What is the conversion formula? Z is equal to, the conversion formula will make, if x is Gaussian with finite mean, mu and sigma squared, I can always do a transformation to get z, which is standard normal. And what is the transformation? X minus mu by sigma. Then z will be standard normal. Other way also it should be possible. So the other way is sigma z equal to x minus mu, or x is equal to mu minus sigma z. Okay. So what it means is, we have a standard normal variable. Sigma mu plus mu z is equal to x minus mu, and then mu plus sigma z is equal to x. Okay. So what it tells is, if z were a standard normal, okay, z, if you do this one, z will be n of 0, 1, whereas x is n mu, sigma. If z is n 0, 1, this transformation will change it to x, which has a finite mean and finite variance, sigma square. Okay. So having got this one, which is the characteristic function for standard normal one, we can arrive at the characteristic, sorry, not characteristic, momentarily. We will come to the characteristic function after that is, what we are looking at is x. We have been using x only so far for standard normal. X is n 0, 1. Is that what? So here I have changed. We don't need to. This is we have been using x here for standard normal, here for a finite group. That doesn't matter. So okay, x is, let us say, n of 0, 1. We want for, let us say, here what we are having z. We will do this one. We will look at this convention. So h z is normal with 0, 1. X is n with mu sigma. Okay. What we know from this one is, we will forget about, we will take only the formula. We know that psi z of t. The moment generating function of z, which is standard normal, has been derived. It is 1 over root of 2 pi e power of minus, where is it? This is what it is, t squared by 2. This is 2, 1 over 2 pi not belong, e power of minus
plus
t squared by 2.
सर प्लस की
Or plus t squared by 2. So we know that for standard normal distribution, the moment generating function takes the form e power of t squared by 2. Now we want it for x. For x is of this one. So psi x of t. For this one, we are looking for the moment generating function. Anyway. That is what the expectation of e power of xt. But how do I get for z? For x is related to z using this formula. So in place of that I can put into t, mu plus sigma z into t I can put. So that is what we get. Okay. So e power of mu t into this one. We have to take expectation with respect to z now. E power of mu t will be there. This is what we have to do. But what if you look at this one? That z is unit normal. We know that how it will look like is that expectation of e power of unit Gaussian distribution into t is what we have done. That will be of the form t squared by 2. The only difference is instead of z into t, that is what we had earlier, we have sigma z is coming. That is the only difference. Okay. So one lab it will be r sigma z is coming, or z into sigma t is coming. So the only difference is that is you will have e power of mu t into e power of sigma squared t squared by 2. Because instead of just t, we have got sigma t is coming. So that has to be squared by 2. That is the only difference we will do. So this should be the MGF for a Gaussian distribution with finite mean and mean. So that can also be written as e power of minus e power of plus mu t plus So now we will summarize. X is normal, mean mu, sigma squared union. Then psi x of t is e power of mu t plus sigma squared t squared. So this will be the, and to cross check whether this is the MGF, the acid test is to get the moments back and convince ourselves these are the moments which we are expecting. So psi dash x of That is, you differentiate once with respect to t, this function. So if you differentiate this one, e power of mu t plus sigma squared t squared by 2 into you have to differentiate it with respect to t. So mu will be that plus this one will be 2 sigma squared t squared by 2. Sorry. This is what you will do. And if you differentiate it twice, this immediately you can say that this and this will go. I will also write it. So again, if you differentiate it, if you again differentiate it, keeping this constant and this ones, you will get and another thing, keeping this constant that we differentiate it with respect to t once, this goes away and here you will have only sigma square. Now, for getting moments, so we know that m1, what is it? E of x is what? From MGF. What is the first moment, which is the expectation of x? How do we get it? We can get it from this by substituting t is equal to 0. So if you substitute 0 for t, you will see that this is mu only, this goes away. Here if you substitute t, it's all zeros into e power of 0 that is equal to 2. So you have got m1 correct. We will look at m2 is equal to 0. So you have to substitute 0 of here, the second equation. If you substitute t is equal to 0 here, this goes away, this mu is there, mu squared will be there. This will be mu squared, and if you substitute t is equal to 0 here, this is e power of 0, that is 1 only. And if you substitute t 0 here, this is just a factor 1, you will have sigma squared. T is equal to 0, e power of 0, that is 1 sigma squared. Here again, just this factor is 1, but here t is equal to 0, so it is mu squared. So what is variance of this? m2 minus m1 squared, right? Second moment, e of x squared minus e of x squared. So that at the end of this one I have finished the derivation of variance. So variance again we get that sigma square, which is what we expect for the Gaussian distribution. So the NGF for the Gaussian random variable turn out to be like this one, and it can be used to for various other things. This is just only for a simple way of convincing ourselves that we are on the right track. Then so once we have this, then other thing we have already, I think I have already shown that if z is equal to x plus y, where x and y are independent random variables, then psi z of t equal to psi x of t into psi y of t. The NGF of the sum is the product of it. So we will just check that on what will happen for this one. That is what we told for if z is equal to x plus y, where x y are Bernoulli with p, then z is binomial with n is equal to 2 comma p, and psi z of t will be the psi x of t will also be the same as psi y of t. For Poisson, it is e power of lambda into e power of t minus t. Okay? Well, even we can do one thing. They need not be identical. I will change that also. If x is Poisson with lambda 1, y is Poisson with parameter lambda 2, then psi x of t is e power of lambda 1 e power of t minus 2, and psi y of t is e power of lambda 2 e power of t minus 2, and psi z of t is psi of x plus y of t is the product of these two NGFs. It can easily be seen that e power of, you can lambda 1 plus lambda 2 into e power of t minus 2. And NGFs are also unique in the sense that if two random variables are the same NGF form, they are the same distribution. And which tells that z is also Poisson. This parameter lambda 1 plus lambda 2. And similarly, if x is normal, mu1 sigma 1 squared, y is normal with mu2 sigma 2 squared. Okay. Again, you can go to the right from the beginning. You can find z is equal to x plus y. You can do expectation of psi z of t. The expectation of e power of zt. It is expectation of e power of x plus y into t. Again, you can do right derived from the first principle also. What is this? It will be into this is again a joint distribution of x and y, where x and y are Gaussian. I will also in addition that they are independent. So what is the joint distribution of two independent Gaussian random variables? It is 1 over 2 pi. Root of 2 pi becomes 2 pi into e power of minus x minus 1 half into x minus mu by sigma 1 the whole square into mu x or sigma 1, or we are calling it as mu 1 sigma mu 1 into y minus mu 2 by sigma 2 the whole square dx dy. Like that we can put and then compute it, but we can, for 2 MGF we can always write it as what? We use that, this is the formula for a single Gaussian random variable. So psi adder of 0 will be e power of mu1 t plus sigma 1 squared t squared by 2 plus mu2 t plus sigma 2 squared t squared by 2. Okay, so that you can plug it as e power of mu1 plus mu2 into t plus sigma 1 square plus sigma 2 square into t square by 2. Like that I can plug it. Which tells me you have a form for MGF which looks this same as the form of a normal distribution. So therefore Z should be normal. Therefore Z should be normal with mu1 plus mu2 and variance sigma 1 square plus sigma 2 square. So we can extend it for n dimensional Gaussian random vector. We will deal with the random vectors later. Well, this is all about the moment generating functions. We have looked at the probability generating functions, moment generating functions. Now we will look at the other transformation, which will also be quite useful. That is the characteristic function. So we will use maybe the same symbol psi. Okay. The random variable comes as the substrate, and the transformation variable we will call it as omega. Sometimes we can call it as I omega because it comes like that. It is nothing but expectation of e power of, you had the random variable x multiplied by s, the transformed variable. T was the original one, tx was there. Now t is purely imaginary and we will denote it as I omega. So it is I omega. So what we are doing is that T is I omega. In an MGF, if you substitute I omega in place of T, you will get the average. That's it. So it is expectation of e power of I omega. So for a continuous one, it is dx. And for a discrete one, That is, the random variable x takes discrete values x1, x2 and so on, where k is the index. Then summation over all such k's, e power of I omega x k into property x equal to x. It's a very similar way of defining for continuous and discrete. So that is the characteristic. And this should look familiar to you. But for the minus sign, this will be very similar to the Fourier transform. So Z transform, everything will be very similar, but only thing is minus. Which means that once you get the characteristic function of x and derive it for some random variable, if you want to get the density function, you take the inverse transformation. Then you will get the fx of x. So, for in this case, it will be e power of minus I omega x dx. That's it. So, this characteristic function, if you do this transformation, this is to be done for this transformation. Then you will get back the density function of the random. So, we saw that you will have a number of random variables, you will define a random variable which is sum of something and so on, which is as such difficult to find through convolution. You get NGF of x, which is sum of from random variables or something else. Then finally, to get back the PDF, you can do the inverse transform. We will try to look at a problem which we already solved using the conventional method of convolving two uniform random variables. What we did is, let x is uniform between minus a by 2 to plus a by 2. Y is uniform between minus a by 2 to plus a by 2. And z is equal to x plus y. We are interested in z and z. This problem we solved through convolution. Now we will use NGF for doing that. So what is this function? We gave a name for it. 1 over this function is 1 by a rect of x by u. This is also the same 1 by a rect of x by u. So what is that rect function? It is centered at x of bit a, and rect function has bit a of unit height, but we will make the height 1 over a so that it becomes normal. So at at x, whatever, if it is 0 at x, this will be 0. So of bit a symmetrically around x, so minus a by 2 to plus a by 2. So this is the x, similarly it's given. So what we have to do is, first we have to find psi x of omega, which is the expectation of. We will use the characteristic function for compute for that. Into between minus a by 2 to plus a by 2, fx of x is just 1 over a. So this is what we have to find out. E power of and so on. Actually, if you use this one, it will just turn out to be what I have written it as here. Sin A omega by 2 by A omega. Because it will be e power of plus I omega A by 2 minus e power of I omega A by 2 e power of I theta. You have to use the De Morris principle law, and then you will see that it is nothing but the sign. After that, this is for x. Similarly, you have got for y also. If fx is same, so the characteristic function is unique. That will also be of this form. So psi z of t will be a square of this. And if you want fx, fz of small z, you have to take the inverse transform of this. How do we do it? That is what is being done. 1 over root of 1 over 2 pi minus infinity psi z of e power of minus. When you take inverse, it has to be minus j omega z d omega. Now from omega domain we are coming to z domain. And if you do that one, this is what you would get. That is by looking at the Fourier, you have to do the transformation, or you can have tables for Fourier transformation using that. And of course, if you plot it, it will be very similar to what we have already got. So it will be, I think, minus a plus c. It will be like this. This will be a by 2 only. Similar to what we have. So the function should be of similar. So that is one of the advantages of the characteristic function. There are some more things that you can also do. Yeah, another thing is, we will just introduce, you can have joint density functions, joint cumulative distribution functions have been defined for random variables which are related to each other. How? F, x, y of x, comma, y, and so on. In a similar manner, joint moment generating functions can also be defined. That is psi x comma y. Psi x of t is what we have been using as the MGF of the random variable x, where t is the transformed variable. Okay. So if there are two random variables, see, they are not sum and up, they are just two random variables, then if you want to find the joint MGF, it will be a function of two dummy variables. One is t1, another is t. One stands for x, another stands for y. And that is defined as a similar expectation of e power of xt is what we, how did we define it? Expectation e power of ex. Here we should have expectation of e power of t1x plus t2. This is how we have to do. T1x plus t2. And if x and y are independent, this MGF will also come. And then what will happen? If you want to get the moment of x, okay, expectation of x, then you have to differentiate this. How do we get? You tell me. How do we get the moment of x? First moment of x. Huh? You can boldly generalize, and it turns out to be there. If I have to get the moment, first moment of x here, what did we do? Differentiate and set t is equal to 0. Similarly, here also you have to do it. But I want moment of x only, not y. So I have to differentiate this with respect to t1 and set t1 is equal to 0. We can further generalize. If you want the nth moment of x, you differentiate it with respect to t1 only, n times, and then set t1 is equal to 0. Similarly, it should be true for t2. If I want the joint moment, that is expectation of x power n, y power m, the trick will be obvious. Partial differentiation of m plus n by tau t1 power m, sorry n, to t2 power m of psi x y of t1 t2 at t1 is equal to 0, t2 is equal to 0. I think here also, I think you have to put t1, t2 also equal to 0, because you cannot leave it as it is. But if you don't differentiate, if you simply put t is equal to 0, you will not have any effect. It will simply give. If you simply substitute in the, okay, if you simply substitute t is equal to 0 here, it will become simply what? It will give 1 only. So if you don't want t2, you want only t1. So after differentiation you set t is equal to, that t is equal to 0. You simply put t2 is equal to 0, t2 will go away. Otherwise it will be a function of t2. So here this is what you have to do. M plus n, this can be doing anyway. This x power n is that, so t1 power n, y power n, t2 power n. If you do this one, you will get this. This is how the joint MGF can be derived. Joint characteristic functions are also there. You get it in all flavors, vanilla, chocolate, everything. So joint characteristic functions can be there. For Gaussian random variables also, we can have so psi x y of omega 1 omega 2, because two Rabi random variables like that we have. So for Gaussian randomables, we can actually compute. But only thing is, we saw that it will be e power of t squared by 2 for MGF. But in characteristic function, I is there. I omega has to be squared. So it will become minus. That is the only difference in that. So it will be e power of, in this case, minus omega 1 squared by 2 into e power of minus omega 2 squared by 2. This will be the joint characteristic function of the normal random irreducible circuit. Okay. Yeah. So if you do an inverse transformation, of course, yeah, it can also be different. I is that is something that we have to do. So I will stop.